Dear students, let's continue our practice on Mathematical Analysis 1, and today we'll begin with you the new section, Indefinite Integral. So today's topic is primitives and indefinite integral. So first of all, let's give a definition to indefinite integral. So if f of x, the function f of x, is definite and continues on the interval any ab, then if f, capital F, the derivative of capital of f of x is equal to fx, then integral f of x dx equal to capital F of x plus any constant c. Here the capital F of x we call primitive of function f of x. So now you can see here it should be satisfy this condition. So the derivative of the primitive equal to the function. And in this case, we can define indefinite integral here. So here c is any arbitrary constant. Arbitrary constant here. So now let's give basic rules of integration. So firstly, integral of constant times f of x dx, it is a integral f of x dx, where a is constant. So this is first basic rule. The second one is the sum, the integral of sum, it is f1 of x plus f2 of x dx. We need to put here dx, differential of x. So it is, if here minus also, we can write like the sum of integrals. So integral f1 of x plus minus the integral, here dx of course, f2 of x dx. So this is second basic rule. Now next one, so here if we change our function, for example, so f, let's write this one, integral of f here, for example, ax plus b in argument, ax plus b dx. So it will be 1 over a big F primitive ax plus b and plus c, of course. So we need to add every time this constant c in indefinite integral, because here we get the family of solutions. For example, if we have any function as solution, so we can add or subtract this constant and get any other one. So here infinitely many solutions we will get. So this is we call family of the solutions. So and that way we need to add this constant to indefinite integral. In indefinite integral, we will not get exactly one solution. Okay, now here of course a is not equal to 0, of course, because it will be in the denominator. So now let's give a table of standard integrals. So we have the table of derivatives of elementary functions, and now we'll write the here table of standard integrals. So let's begin with the first one. So it is the integral x the power of n dx, power function here. So, and what we will get here, so it will be x n plus first degree over n plus 1 and plus c. Here n is not equal to minus 1. This is main condition. So now let's check it. So how to check it? We wrote the derivative of primitive should be equal to f of x, and this is very useful to check our answer solution. So for example, here if you want to take a derivative, this is primitive of our function. If you want to take a derivative here, so what we get here, n plus 1 times x n plus 1 minus 1 over here we have n plus 1, the constant, yes, and they are cancelled and we get just x the power of n. So this is and we showed that the derivative of primitive is equal to our function x the power of n. So now the next integral, it is the integral x the dx over x. Let's do it, dx over x. So it will be natural logarithm of x plus c, of course. So the third one, I will write the main ones. Okay, now it is, for example, which one? Let's do dx over integral dx over x squared plus a squared. This is 1 over a arc tangent x over a plus c. So next one, number 4. So here we have, for example, if we have minus between them, x squared minus a squared, this is 1 over now it will be 1 over 2a natural logarithm of x minus a over x plus a. We can solve these examples also and get these answers plus c. And the next one, for example, the next one is a the power of x dx. So it is a the power of x over natural logarithm of a and plus c. And in particular, here we have e the power of x. It is e the power of x plus c. Because of the derivative of e the power of x, it was e the power of x. That's why here also the same one. And now trigonometric functions. So number 6. So it is sine x here, for example. Integral sine x dx. So it will be minus cosine x plus, because of the derivative of cosine x, it is minus sine x, and here we have minus, it will be just sine x. So it's very easy to check it. Now next one, cosine x now. So it will be now sine x, because the derivative of sine x is just cosine x. And the next one, so we have other ones also. 8. For example, we can write here dx over which one? Let's do cosine square x. Dx over cosine square x. This is, it will be tangent x. Or here, number 9. Let's write here. So the same one, dx over sine square x now. It will be now minus cotangent x plus c. And we have also hyperbolic functions. So sine hyperbolic dx, it will be cosine hyperbolic x dx plus c. And for example, cosine hyperbolic, the integral of cosine hyperbolic x, it will be sine hyperbolic plus c. So they are the table. They are the main elementary functions of integral of elementary functions. So integrals of elementary functions. Now we'll move to the examples. Okay, it's given a cubic polynomial, and we need to calculate the integral of this polynomial. So we will use our first basic function. So x to the power of n. So let's recall one more time. The x to the power of n dx, it was x n plus first over n plus 1 plus c. So now we will use it, and here, and of course we will use the property of undefined integral. So if you remember, the integral of the sum f, for example, f1 x plus f2 x dx, it's equal to the sum of integrals. So f1 of x dx plus integral f2 of x dx. So now let's try to solve this example. So it is, let's continue here. Now let's use this property and write separately each function. So it will be integral of ax cubed dx plus integral of bx squared dx plus the integral cx dx and the plus integral d dx. So now and now we will use this one. So we will get the answer here. So it will be a, and of course here we need to use one more property. So integral of a f of x dx, it was a integral f of x dx. A is constant, yeah. So now we need to use this one, and here dx, we have dx. It's not visible. So dx. Okay, so now we will use it, and a x cubed dx plus b x squared dx plus c x dx, and plus d integral dx. Okay, and now we will calculate each this integral. So it will be now a times so it is x fourth over 4 it will be, yes, because we will use this property, this table. So, and we get here as answer x fourth over 4 plus 1 and over n plus 1 again. So plus b x cubed over 3 plus c x squared over 2, and look here, plus d, and what we get here we have 0 power, x 0 power, and 0 plus 1 it will be first power, so it will be just x now, dx. So this is not differential, this is just constant dx, and this is, and plus c of course, and this is our solution. Okay, now let's try to do other examples also. Okay, so the next example, for example, if we have let's try to do the next one. So the integral, for example, if you have any polynomials like this, x squared, for example 5 minus x 4th degree dx, so we can solve this such kind of equation, such kind of integrals as opening these brackets and get the polynomial, and after this we have these properties, and using these properties we can find this integral like the previous example. So I think this is very easy. Open this first degree and the times x squared. And now I want to show other one. So the integral 1 minus x over x the power of squared dx. So here firstly we need to rewrite this function 1 over x minus 1 squared dx, and now we can open these brackets by the formula a minus b squared, and here we'll get the integral. So it will be 1 over x squared minus 2 over x and plus 1 dx. And now if we continue, so 1 over x integral of 1 over x squared dx minus integral of 2 over x dx and plus the integral of dx. The next time I will try to write directly, not open this each one. I think it will be clear now. So, and now what we get? This is minus second degree. So minus 2 plus 1 will be minus 1 over minus 1. So we get minus 1 over x here. One more time. So look here. 1 over x squared, the integral of 1 over x squared, it is dx. It's x minus second degree dx, or it will be now x minus 2 plus 1 over minus 2 plus 1 plus c. Is it clear? Now, minus 1 over x, here we have 2 over x, so it is minus 2, integral of 1 over x, it was natural logarithm of x, and the last one, it's just x plus c now. So this is answer. Okay, now let's continue our example. So the next one, it is integral of 1 minus 1 over x squared times square root of x dx. So what should we do here? Here again, we will open these brackets, and it will be, so this is x third over 4th degree. So times 1, it will be x 3 over 4th degree. And the minus here, 3 over 4 minus 2. So here we have like this. Here x 3 over 4 over x squared. And if we subtract it, we get, so look here, it should be, it will be clear, look here. So 3 over 4th degree and second degree, and we will use this this property of exponents, and we need to subtract this 2 degrees. Yes? So we have, if we continue, integral x 3 over 4th minus x 3 over 4th minus 2 dx. And now we get the x 3 over 4th minus x minus 5 over 4th dx. Okay, and now we can continue and find our solution. So here x 3 over 4th plus 1 over 3 over 4th plus 1. Then minus x minus 5 over 4th plus 1 over minus 5 over 4 plus 1. So plus c, of course, and it will be now x 7 over 4 and 7 over 4 here, so 4 over 7 x 7 over 4, and here we have negative 1, so it will be plus now in the middle, and minus 1 over 4 we get, so x 4 x minus 1 over 4 and plus c. And this is the answer of our example. And let's move to the next example. So integral x squared over 1 plus x squared dx. How to solve this example? So here, if you remember, we have the integral dx over x squared plus a squared. It was 1 over a arctangent x over a plus c. So in particular, if instead of a we have 1, we get dx over x squared plus 1, and it will be now just arctangent x plus c. So look here, the denominator is same, but in numerator we have x squared, so we need to use this formula, and we will need to provide to this formula. And how? So now we have here x squared, and if we add and subtract 1 from numerator, x squared plus 1 minus 1 over x squared plus 1, let's write it, dx. There's no changing in our example because we add 1 and subtracted 1. So, but now we can divide. Yes, so we call it taking integer part of the function. So here we have now 1 minus 1 over x squared plus 1 dx. So, and now this is integral of 1, and this is integral of 1 over x squared plus 1. It gives us arctangent. So it is x minus, using this formula, arctangent x plus c. This is answer. Okay, and now one more example. So using again the table. So let's try to find the next one. Exercise number 5. So integral to the power of x plus 3 the power of x squared dx. So let's find this integral, and to find this integral, firstly we need to open these brackets. Integral to 2x plus 2 times 2x 3x plus 3 2x dx. And so hence we get integral for the power of x plus 2 times 6 the power of x here in the middle, and plus 9 the power of x dx. And now let's use our table. So ax dx, it was a the power of x over natural logarithm of a plus c. So we will use our table of integration and find this one. So now it is 4 the power of x over natural logarithm of 4 plus 2 times 6 the power of x over natural logarithm of 6, and plus 9 the power of x natural logarithm of 9 plus c. This is answer. And now let's move to the next example. E to the power of 3x plus 1 over e to the power of x plus 1 dx. So here of course we need to use the table again. So e to the power of x dx, it was just e to the power of x plus c. But here we have the fraction, so e to the power of 3x plus 1. And in this case, in the bottom, we have e to the power of x plus 1. So let's recall the again sharp multiplication formula. So a cubed plus b cubed. So we can write it like a to the power of x cubed plus 1 cubed over e to the power of x plus 1 dx. So now if we open by the formula, we have e to the power of x plus 1 then e to the power of 2x minus e to the power of x plus 1 over e to the power of x plus 1. So dx. And now we can cancel them. So, and we get the integral e to the power of 2x minus e to the power of x plus 1 dx. Hence, using table of integration, we'll get here 1 over, but here we have 2x. So that's why we have 1 over 2 here, e to the power of 2x, and the minus, because here in the middle minus, e to the power of x and plus x plus c. This is the answer of our example. The next example, so integral of 1 plus sine x plus cosine x. So now we will use the table for sine and cosine. Integral of sine x, it was minus cosine x plus c, and the integral of cosine x dx, it is sine x plus c. So we will use this table, and here we have the integral of 1, it's just x, and the next one, it is integral of sine x, this is minus cosine x, and the integral of cosine x, it is sine x, so plus sine x plus c. This is very easy. And let's consider the next example. So integral 2x minus 3 tens power. So here, if you want to solve by the polynomial, we need to open this tens degree. And we can solve this tens degree, but it will be more difficult. So now, we have, let's recall this property. Integral of f ax plus b dx was 1 over a, f primitive, so ax plus b and plus c. So let's use this property now, and here what we have. So this is, look here, and our function is power function. So now we will do it. So using this formula, it will be, so 2x minus 3 10 plus first degree over 10 plus 1, and of course 1 over a, our a is 2, so it will be 1 over 2 times 1 over 2 plus c. So if you continue, we get here 11, 2x minus 3 11th degree over 22, 2 times 11 plus c. This is correct answer. And now let's move to the next one. 9. So here we have another example. For example, dx over square root of 2 minus 5x. So here again we need to use this property and find it. So this is 2 minus 5x. It is 2 minus 5x the power minus 1 over 2 dx. integral. So our a is minus 5 here. So the answer is minus 1 over 5, 1 over a. Look here. And the primitive of this function now, it will be 2 minus 5x, the power of, this is power function, minus 1 over 2 plus 1 over minus 1 over 2 plus 1. So it is 1 over 2, 1 over 2, here, of course, plus c. And if we continue it, so we get, so it is 2 minus 2 over 5, 2 minus 5x, 1 over 2 plus c. This is correct answer. This is correct answer. Okay, let's continue. And the next example is the following integral, dx over 2 minus 3x squared. So here we need to use from our table the following one. So recall dx over x squared minus a squared. This is 1 over 2a natural logarithm x minus a over x plus a. If in the middle we have minus, plus c, of course. So now let's use this integral to define our integral. Okay, now can we factorize this denominator? Yes, of course. So we need to factorize it. 1 over 2 take out from the brackets, and we have dx over here 1 minus, and now here we have square root of 3 over 2 x squared. We need to provide to this form x squared minus a squared. So this is x squared and a squared. This is a is 1 in our case. So now what do we get here? So if you continue, and now we can use this formula. It is 1 over 2 times, so now this is a, yes, 1 over 2a it should be. So 1 over 2 and a, our a is square root of 3 over 2. And times natural logarithm. And now look here. However, this is opposite 1. So it is 1 minus x squared. And it will be the opposite one. So not x minus a over x plus a. Now it will be x from the property of natural logarithm. X plus a over x minus a it should be. So 1 plus a and 1 minus a in our case. So 1 plus a, it is square root of 3 over 2 x over 1 minus square root of 3 over 2 x in absolute value. So again, it is 1 plus square root of 3 over 2x over 1 minus square root of 3 over 2x, and plus our constant c. If we simplify it, so we get here so it will be now, let's simplify it, square root of 3 over 2, or just they are cancelled, not cancelled, because we have square root of 2 here, so they are not cancelled, and it will be 1 over 2 square root of 6 now, and natural logarithm. Here also we can take out, that's why it will be 1 over 2 square root of 6, and so it will be 1 after simplifying. Now not 1, now square root of 2, because of we take out square root of 2 here also in denominator. So square root of 2 plus square root of 3x over square root of 2 minus square root of 3x here times in absolute value plus c. This is answer. Okay, now let's continue. And the next one, it is exercise number 11. So here we have integral dx over 3x squared minus 2. Let's calculate it. And no, here not 2 minus 3x squared. Let's consider 2 minus 3x squared plus 2 minus 3x squared, like this, dx over 2 minus 3x squared. So here we'll use for formula for arcsine and arc cosine. And let's recall the formula. So integral dx over square root of 1 minus x squared. This is arcsine. Arc sine x plus c. We will use it now. So squared here, squared. So we need to provide this form 1 minus x squared. So here we have 2, and we have square root of 3 also. So this is a, yes, and we need to again factorize it. This is our denominator, and what we get here, so it's again 1 over a. So like this, dx over 2 minus square root of 3, here square root of 2 squared, and the minus square root of 3x squared, like this, and all of them in square root. So now, let's continue it. So we get here, it is a, our a is square root of 3, so it will be 1 over square root of 3, 1 over a, arcsine, and this one. So it will be in generally. So e square root of 3 over 2 in square root of x and plus c. This is in generally. So if you want to write our formula in generally, so it will be square root of dx over a squared minus x squared. So it is 1 over a, 1 over a, and then arcsine, so here we have ax squared in this case, b squared minus ax squared, like this, b squared minus ax squared. So it is 1 over a arcsine and a over b here, a over b x plus c. This is answer. And the next example, so calculate the integral dx over 1 plus cosine x, compute it. So here, what should we need firstly? Use the trigonometry formula. So if you remember, 1 plus cosine x, it is, let me write here, 1 plus cosine x, it is 2 cosine x over 2 here, or 2 cosine square x over 2. Cosine square x over 2. So here, now, we replace our 1 plus cosine x with this one, and we'll get dx over 2 cosine square x over 2 with half angle. And now, it is, if you continue, integral. So here 1 over 2, just dx over cosine square x over 2, and let's recall again that our table of undefined integrals. There we have the next one. So integral of dx over cosine square x, this is tangent x. So now let's use this one, and we have here just tangent 1 over 2 tangent x x over 2 we will get. X over 2. X over 2, and we have again here the coefficient of x. It is 1 over 2, and it should be 1 over a. Yes, so now this is 1 over 2 times 2, it will be now here times 2, and they are cancelled with this one, and we have just tangent x over 2 plus c constant. And now let's move to the next section. So this is undefined integral using the differential. So we here we have dx, yes, and using this differential we can compute the integrals. So let me write the next example. It is x integral x dx over 1 minus x squared. So here directly we cannot compute it, but if we write our x in our differential, in the inside of our differential, and how it will be, the differential, this is derivative, for example, yeah. So and when in which function, if we take the derivative, we have x. So this is x squared, yes, x squared, and we have 2x in derivative. So we can write it like integral. So here 1 over 2 dx squared. So if we complete the differential from x squared, it will be x dx. dx squared, x dx. So 2x dx, and 2 and 2 are cancelled, and we have just dx, x dx. One more time. So if we compute it here, look here. So dx squared, this is 2x dx. And this 2 we divide here. And we have just x dx here, the given one. So is it clear? So now, here we have square root of 1 minus x squared. So in previous examples, we compute our undefined integrals with respect to x. And in our case, now we can compute it with respect to x squared. Now our variable is not x squared. By this variable, we should integrate our function. So now here, but here we can add this one also, because it's not changing our differential. 1 plus x squared differential is again it's equal to differential from x squared. So here let's add this one. 1 minus, do 1 over 2 integral d to do equal these two ones. 1 minus x squared over square root of 1 minus x squared. But now here we have minus. So that's why we add here minus, multiply minus 1, and everything, it will be okay now. So now equal, and so let's continue. And now we have variable 1 minus x squared. So 1 minus x squared, it is as our x. And here also 1 minus x squared. So this is simple with the integral dx over square root of x. This is same with this integral. So what was the answer here? So it is now minus 1 over 2 times 1 minus x squared, and in which power now? It is minus 1 over 2 plus 1, and here also minus 1 over 2 plus 1. So plus c, of course. And what we get here? So this is minus 1 over 2 minus 1 over 2, and here we have 1 over 2. They are cancelled. It will be just minus. So minus, and here the 1 over 2, of course, minus square root of 1 minus x squared now, plus c. This is answer. Is it clear? So we can do our variable in differential, and then to do useful for us, and then we will integrate with respect to this variable, not this, not x. What inside of in differential we need to integrate with respect to this one. And one more example here, x squared, integral of x squared, cubic root of 1 plus x cubed dx. So here, firstly, look, pay attention, x cubed we have, and x squared we have. So if we do this x squared in differential, so it will be x cubed, because the derivative of x cubed give to us x squared, and yeah, we have the coefficients, but we can do these coefficients, we can divide by this coefficient, and there is no change. So there are no changes we have. And here, so we have x squared in differential. It will be, firstly, this function 1 plus x cubed, and dx cubed. So, and if we calculate the derivative of x cubed, it is 3x squared. And we need to divide by 3, so 1 over 3 here now. And now look here, now we have 1 plus x cubed, and we can add this 1 also here. So it is now 1 over 3 integral cubic root of 1 plus x squared d 1 plus x cubed. So now they are same. And now we can compute our integral with respect to 1 plus x cubed. So it is now, this is just 1 plus x cubed, it is as x our, and it is cubic root of x just. This is same with cubic root of x. So here we have 1 plus 1 over 3 and 1 plus x cubed, 1 over 3 plus 1 over 1 over 3 plus 1. It gives us 4 over 3 plus c, of course, and we have 1 over 3 times here 3 over 4 and 1 plus x cubed, 4 over 3 plus c. They are cancelled, and we have, so we have here just 1 over 4, 1 plus x cubed, 4 over 3 plus c. This is answer. Okay, one more example here. So just a second. So now we will consider the next example. X integral x dx over 4 plus x fourth degree. And now, and here also, look here, this is x, and we can write this x as in differential, and it will be dx squared as x squared, and of course 1 over 2 here over, and now look here, the denominator we can write 2 squared plus x squared squared. And what is it? This is formula. Look here, and now our x, our variable, it's not x, our variable now x squared. This one is our variable. And now here we have x squared squared. So it is a squared plus x squared with the formula for arctangent. Now it's 1 over 2, but in arctangent formula also we have 1 over a, so this is again 1 over 2, and arctangent, now x squared over 2 we have plus c. So we use the formula for arctangent. Again, one more time, let's recall it. Dx over a squared plus x squared. So it is 1 over a arctangent x over a. So now we have this following answer here. If we simplify it, it will be now 1 over 4 just, yes, and 1 over 4 arctangent x squared over 2 plus c. This is final answer. This is final answer. And let's continue. So the next example is the compute integral sine 1 over x times dx over x squared. So here again we will use this rule of differentiation, and here we have dx over x squared, and but in our in variable we have 1 over x in sine. So we need to equating these two variables using differential. So we can write this 1 over x squared because of 1 over x squared derivatives is 1 over x derivatives, otherwise, yes, of course, 1 over x derivatives, it is minus 1 over x squared. So we have this equality, and if you use it here, it will be now integral sine 1 over x, and now here we have in differential 1 over x. So it gives us minus 1 over x squared, but we don't have minus. That's why we will add here minus. Multiply by minus here. So now, and our variable now it's 1 over x just. So sine 1 over x, it's as sine x. Sine x dx. Like this we have. So the integral of sine x, so primitive of sine x, it is cosine x minus cosine x. That's why here we have minus, however it's minus cosine x, minus we have plus cosine 1 over x plus c. This is answer. Okay, now, and let me write another example. So here we have next one. So integral x times e to the power of minus x squared dx. So, and how to solve this one? Here also we have x here, and we can do it in differential x squared because of, again, the derivative of x squared, this is 2x. That's why here we have integral e to the power of, let's do minus x squared in differential, I mean. So d minus x squared, and derivative of this one minus 2x. That's why we need to divide by minus 1 over 2 here. And now we have just e to the power of x, the integral of e to s e to the power of x. So it not x, our x now x squared minus x squared. So the answer is minus 1 over 2 e to the power minus x squared plus c. This is answer. And the next example, so number 18 now we have. The next one is, let's do this one, natural logarithm square x over x dx. So I took an example from the book of the Meadows. And ln square x over x dx. Here, what should we do? Look here. Here 1 over x we have, and if you write 1 over x in differential, it will be natural logarithm of x, and we get the same one. So natural logarithm square x, and in differential, natural logarithm of x. So, and now here we have two natural logarithms, natural logarithm of x and natural logarithm of x here in differential. So we need to integrate with respect to this natural logarithm. And this is now power function. It will be natural logarithm of x 2 plus 1 over 2 plus 1 plus c, or 1 over 3 natural logarithm cubed x plus c. Okay, now, and let's do the next one now. Integral of sine 5x cosine x dx. So here fifth power, and now again we'll use this rule of this differentiation, and here we can write cosine x in differential, and it will be integral, so sine fifth power of x, now differential of sine x, and differential of sine x, this is cosine x, and we have this cosine. Now it is integral of sine x, so we can easily find here, this is power function now, and our variable, it's not now trigonometric function, our variable is just sine x, and our function is power function. So this is again sine x, this as previous example, sine x of power of 5 plus 1 over 5 plus 1 and plus c, or answer is sine 6 power of x over 6 plus c. And let's do the last one. So let's compute the tangent x. Let's compute the tangent x. So here we have integral of tangent x dx. This is, so tangent x, it's sine x over cosine x. Yes. So now we can use this again, this property, and sine x right in differential, and it gives us d cosine x, but differential of cosine x, this is minus sine x, so we don't have here minus, that's why we need to multiply by minus here, over cosine x, and now we get like dx over x. So it is natural logarithm of x, yes, but our x, it's cosine x. So the answer is minus natural logarithm of cosine x plus c. So, and this is the final answer here, minus natural logarithm of cosine, minus natural logarithm of cosine x plus c. So I think it's clear how to work with elementary functions, with integrals of elementary functions, and we have table of integrals of elementary function, so it is very useful for us to find the integrals of elementary functions. So we will continue the next time the topic integrals. Thank you for your attention. If you have any questions, you can connect with us in our discussion group. Thank you for your attention.